everyone. I'm Sivaganesan Danushkanda, and you can call me Skanda for short. Today I'll be presenting the research paper on model-agnostic meta-learning for fast adaptation of deep networks. So this is the overview of my presentation. I will talk a little bit about the problem, its challenges, and basic concepts. I will also show why the model-agnostic method can be used for different types of algorithms like classification, regression, and etc. Then I will move into a few shots the different types of datasets used, and finally I will conclude with the results. But mostly I will spend more time on showing the implementation, the results, and the conclusion. So first let's talk about the human intelligence. Humans are able to recognize objects from a few examples and learn new skills after merely minutes of experience. So meta-learning is inspired from human learning, which focuses on understanding one's own learning and learning processes. So if you have learned like 100 tasks already, can you figure out how to learn more efficiently? Like having multiple tasks is an advantage here. So it simply refers to learning to learn. Few-shot meta-learning is a concept that basically trains a model to adapt quickly to a new task with few data points and training interactions. The basic concept is that when you are given a set of characters, by looking at them, few shots should basically say that, okay, if I give you this character, can you build a model that can identify a similar character but elsewhere and identify it as the right character or if it's a totally wrong one. So it can also be applied to classification and regression type of problems and policy gradient reinforcement learning as well. So the model is where you can easily learn and get the data by giving only a few data points and keeps further improving on the small data that you feed it. The more you feed it, it gets better. But we have to be careful to avoid overfitting of data, and we do not want to prejudice the results. What we can do is to train each task in sets of so-called batches, and once your training starts, it improves the method for each task. So in the model, we are introducing a model parameter that can be applied with gradient steps. So in the paper, the author is using one gradient step, but we can, I think, use multiple of them to get a summation and can use to better improve the meta-learning algorithm. The data that represented is called the meta optimization component that is used to optimize the model. So specifically, it learns from smaller number of gradient updates, which means fast learning on a new task. So this is an illustration of the model-agnostic meta-learning algorithm. So 1, 2, 3 are the three different tasks, that is, and theta is a parameter. We need to find a point where the distance between the point and these 3 points, theta 1, theta 2, and theta 3, are closest, so it's easy to adapt to new changes. So like I said previously, at first, if we give a set of images to anyone, like say a child, he or she can identify the similarities between them, right? So now, if we give a different image, the kid can identify it as a different image from the ones he or she saw from the previous set. So we're just giving a set of sample data and we are letting them figure out the task. So we should also make sure to give a handful of sample or we run into overfitting problems. So the paper focuses on image classification of the model. In the paper, the dataset used is the Omligot dataset, which contains around 1623 handwritten characters from 50 alphabets for image classification. Each of these characters have 20 different handwritten characters using the Amazon's Mechanical Turk. So explaining some of the terms, meta-learning is nothing but learning how to learn. So basically learning how to learn the task. Model-agnostic is the ability to apply this model across various other types of problems. So this is the sample of the characters in the Omniglot set. You can see different characters and various variations of those characters as well. I'm going to skip this previous work and circle back to it if time permits. Okay, so the main idea, so basically what makes this model-agnostic meta-learning generic to model learning problems is the way in which it receives the task. So the task has four components, which comprises of the loss function, distribution over initiation, initial observation, transition distribution, and episode length. So the loss function depends on the type of problem because there are different algorithms. There is a basic algorithm for meta-learning, then there is a derivative from the basic to mainly capture a few shots. The reason why it is generic is because you can apply the stochastic gradient descent for the learner and for the few shots classification which may focus on. Here you can either apply cross entropy loss or use the mean square root error for regression problems. So the paper introduces three algorithms, model-agnostic meta-learning algorithms that are similar but applied to various focuses. The base class in which the model-agnostic meta-learning can be used for generic tasks. The rest of the two are more direct ones. So MAML, which is model-agnostic meta-learning, is used for few-shot supervised learning, and the algorithm 3, MAML, is used for reinforcement learning. So here you can see the algorithms for the models 1 and 2. In my final project, I am planning on concentrating on algorithm 2, the MAML for few-shot supervised learning. With algorithm 1, which is the base class, we start with some initial parameter. Then you give it some task and you play around with some of the tools, and using TensorFlow, we try to generate a NumPy array. This is performed to get the basic batches I talked about from the earlier image. From the earlier slides, these batches are taken from the image generated. Now we are going through each batches of tasks and use the stochastic gradient to compute the assumptions. So step 8 is where the meta optimization across tasks is performed using the stochastic gradient descent. So the model parameters theta are updated here. We then try to get the batches from the image generated. We go through each batch of tasks and use the stochastic gradient here. Around step 10 is where the meta optimization is happening, and it's basically like the gradient of the same data type. Moving on to algorithm 2, it is very similar to algorithm 1, but it has a few data points shown in step 5. The data points have x and y values generated from the task. So two common loss functions used for supervised classification and regression are the cross entropy and mean squared error MSE, which is shown in step 6. Algorithm 3 is similar to algorithm 4. The main difference is in steps 5 and 8, where it requires sampling trajectories from the environment corresponding to the task. So in the paper, for the few shots, they used a generic way of classifying using the n-way classification, whereby you can use either 1 or 5 shots. They specifically used n unseen classes and chose 1200 randomly trained characters from the Omniglot dataset. The author also used k different instances for each classes, and for the alpha parameter, he used 0.4 and the batch size of 32. In terms of evaluation, the model gave the ability to classify new instances with n classes. So based on the results, they actually compared several experiments which are not only for the few shots but also other classification algorithms using the Omniglot dataset, which is shown on the top, and they also used the mini image nets, which is shown in the bottom. So they compared this with the mammal population average. With one shot, they had great improvement. With one shot, they had great improvement compared to the convolutional and recurrent models, or the MAN model. We can see that with one shot, we have increased the accuracy from 82.8% to 89.7%, and the same goes with 5 shots, where the accuracy is increased from 94.9 to 97.5. So in conclusion, the model agnostic does not expand the number of learned parameters, nor it places constraints on the model architecture. It can be combined with fully connected convolutional or recurrent neural networks. It can also be used with various loss functions, including differentiable supervised losses and non-differentiable reinforcement learning objectives as well. Model's parameter is trained in a way that few gradient steps or a gradient step produces a good result on a new task. So that is the end of my presentation. I'll be more than happy to take in questions. So reach out to me through my email provided on the bottom of the screen. And thank you, Dr. Sun, for providing me the opportunity to present. And see you all soon. Thank you.